So let's start our second part of this feasibility of reactions using electrode potentials and focus on the exam style questions that we are going to do. They're a little bit more difficult. And basically it's the third one I'm still in pajamas with. You can tell I did this all on one day. Okay, so basically let's go for this one. What's the best reducing agent? Now, you've got to think to yourself, what is a reducing agent first? A reducing agent causes something to gain. Reducing is gaining, so it causes something to gain. So if I have something here and I want you to gain it, I've got to give it to you and therefore I've got to lose it. So you've got to look at the thing that loses electrons, the best. So which one loses the best? So the less positive loses electrons and therefore is the reducing agent. So the one that is least positive and most negative. So that is this one here. So the common mistake is for people just to write Zn2+ because they read from the left. But the less positive loses electrons. So you've got to pick the species here that loses the electrons. And the thing that loses the electrons is not the zinc 2+. That would gain it because it's next to the electrons there. It would gain it and go that way. No, it's the zinc. And that means the electrons, the equilibrium will go towards the left. So if you're in this exam and expected to explain it, say the equilibrium has gone to the left. And it's the zinc solid because it's the only one that can lose electrons. So it's really, really important. Let's go the converse. And let's go for the best oxidizing agent now. And you've got here again, most positive gains electrons and therefore is an oxidizing agent. An oxidizing agent causes something to lose. So if this bit here is losing, I've got to give it there. Okay, so therefore the thing that the other part is gaining. Okay, so the more positive gains the electrons and it is an oxidizing agent. So then we need to flip this and look for the most positive. So the most positive is this one here. Okay, 1.51. Again, we need to look in it and say which part is a gaining. So we're not going to write the Mn2+ because that's not gaining. The part that's gaining is this part here. And here's the really important thing. Your reducing agent is not the MnO4. It is the MnO4 and the H+. Okay, you have to write both things. Okay, really, really important. Again, common mistake is that they just write the thing on the left. Okay, and that is it. And remember that equilibrium is going to the right, which means you're gaining electrons. So the next type of question is based upon if we don't use 1 mole per decimeter. Remember the standard conditions are that you have 1 mole per decimeter cubed solution. So what if we changed it and we increased or decreased the concentration? So I'm going to lower the concentration. I can only change concentrations when I'm looking at the aqueous part of the reaction. I can't do anything with the solid itself, okay? Now, if that's the case, I've lowered that concentration. Now, Le Chatelier says that it will do the opposite of what you apply. So if I'm lowering the concentration of this, the zinc is going to turn into more of it to increase it back up again. So the equilibrium is going to go to the left. Now that produces many, many more electrons. So that will produce many electrons. Because it produces many more electrons, that means this will become more negative. And that's what you need to say. So, and I'll write that out here for you. For the zinc half cell, reducing the concentration of the zinc ions would pull the equilibrium to the left. Okay, that would increase the number of electrons on the electrode and make the voltage more negative. Okay, so you get a more negative result. So really, really important. We then take this and we take this for a different example. Okay, so and that different example is your copper. So I've got copper here. So what I'm actually going to do with this one. Okay, I'm going to increase the concentration. Now, if I increase the concentration of the copper 2+, it's going to want to do the opposite, decrease that concentration. So it's Le Chatelier's again. And that means the equilibrium goes to the right. Now, if it goes to the right, it will gain many, many more electrons. So many more electrons. Now, the more positive this is, it's telling you that the more it gains electrons. So if I've gained more electrons, this will become more positive. Okay, so again, writing that out in a slightly shorter fashion. Okay. Increasing the concentration will pull the equilibrium to the right, making it the electrode potential more positive. Okay, so making it more positive. And that's what happens if you change the concentration of solutions. So this is a really, really difficult question. So let's talk about it. So choosing the acid to work based on feasibility. So we want to oxidize Fe2+ to Fe3+ using acidified potassium permanganate, which is this one here, the manganate half equation. Which acid should be used with it? Because it's acidified potassium permanganate, which means I can either use hydrochloric acid. So this is hydrochloric acid will dissociate into H+ and Cl- ions, or sulfuric acid, which will which will make SO4 2 minus ions. So this is the one for sulfuric acid, and this is the one for the hydrochloric acid. So when we put it in, what we want is we don't want this to interfere with what's going on. So I'm going to say, right, first of all, let's move this down and make a bit more sense. So sulfuric acid will not react with the MnO4 because the MnO4 has to gain electrons to react. Okay? Well, the SO4 has got a higher electrode potential. Okay? So it's got a higher electrode potential, so the SO4 would want to gain. Okay? And the SO4 can't gain anyway because the SO4 can only lose. All right, so we don't have to worry about the SO4 actually reacting with the MnO4. Remember, we're going to react this with iron, and we're going to do a titration. And if we're doing a titration, okay, with it as well, we need to accurately know that all the MnO4 is going to react with the iron. Now we know that if it's sulfuric acid, the MnO4 will not react with the sulfuric acid. Okay, just to make it clear, sulfuric acid will dissociate into this SO4 2-. That's the SO4 2- there. Okay, I'll just repeat that because this is a very difficult question. You want all of the MnO4 to react with your Fe2+. You want all of it in this equation here. You want all of that, that's the full equation, to react with this. Okay? So you don't want any of the MnO4 to react with the acids that you're putting in. Now it won't react with the sulfuric acid because the sulfuric acid has a higher electrode potential. That's what you need to say, a higher electrode potential, which means the equilibrium on this one would be to the right. It would be making more of the SO4 2-, not less, okay, because it's more positive electrode potential. Now, if we then go from this one and we start talking about something else, okay, because we know this is going to go that way and this is going to go that way, okay, let's go to the next one. Now, hydrochloric acid is going to react with MnO4 because it's going to therefore give an inaccurate result. So if we look here, the hydrochloric acid will react with NO4. Now, why? Now, if you look here, the electrode potential here is positive. The electrode potential here is also positive, but less positive. So we think this one's going to lose electrons, and we think that this bottom one's going to gain. Now, remember, we want the MnO4 to react with the Fe2+. We don't want it to react with anything else. So if we put hydrochloric acid in, it's going to react with the chloride ions because the chloride ions are going to want to lose electrons because the electrode potential is less than the manganate. Okay, it's going to want to lose electrons. So the more positive gains electrons, but this one's going to lose electrons. And if that's going to lose electrons, that's going to want to gain electrons, which means this reaction will go to the left and this reaction will go to the right, which uses up some of your MnO4, some of the MnO4 that you wanted to react with the Fe. So it's really, really important on this one, okay, that you can see that difference, okay? And just to make it clear again, remember the chloride comes to make that chloride there, okay? So let's put that in and summarize that. The hydrochloric acid will react with the MnO4, giving an accurate result, and that's your answer. The sulfuric acid will not react. Now, what I'd add to that as well is I'd use the electrode potentials to prove that. And it's really important that if you're given electrode potentials data, you use it. So in this example, we're going to look at which of these reactions can actually oxidize water to oxygen. There's your water, there's your oxygen. So to oxidize water, we've got to make the equilibrium go that way. We've got to make it lose electrons. Now to lose electrons, it must be the most negative electrode potential compared to the other one it's joined with. So therefore, everything that's more positive than it will gain electrons. So if we look here, the chromate is more positive, so that will gain, and this will lose. The chlorine is more positive, so that will gain, and this will lose. The manganate is more positive, so this will gain, and the oxygen will lose. The only one that won't work is the bromine. The bromine wants to lose electrons, and so that would make this gain electrons, the equilibrium go to the right. It wouldn't work. So if we put this down here, and now we know that all of these will work. So all of the equilibrium on these ones will go to the right because they want to gain electrons if they're mixed with the water and the oxygen, okay? But the one at the bottom will not work. Now, all three of these reactions are feasible, as in they could work, but they don't. So sometimes they hit you with this horrible question about why do they not occur. So I'm going to give you the reasons why they don't occur. The activation energy is too high and the rate is too slow. Okay, it just means you have to put too much energy to get it to happen. Okay, the concentrations are not standard. Okay, these are all based on concentrations being standard, so they might not be standard. So there's your two reasons which will enable you to get that mark.